I would like to introduce the first speaker, Marjolein Daeter, and her talk is titled Experimental Data on Partial Melting of an Ilmenite-Bearing Cumulate Layer on the Moon.
Okay, thank you. So hi everyone, this presentation is about my master's thesis at VU Amsterdam on experimental data on partial melting of an ilmenite-bearing cumulate layer in the moon. So this session is of course about surface composition, and while the title may give the idea that my thesis doesn't really fit in, there is a link to the titanium-rich surface basalts found both in Apollo samples and by remote sensing of volcanic deposits on the surface. These titanium-rich samples are thought to be related to a titanium-rich source in the mantle of the moon, and my thesis is about such a potential source. To make rocks rich in titanium, we first have to look at the way the moon solidified from a global lunar magma ocean. As shown in these sketches by Lin et al., upon cooling of the lunar magma ocean, mineral cumulates form different layers. Only the layers that form last, when the ocean is almost all solidified, contain the mineral ilmenite, which is the main host of titanium in the moon. This ilmenite-bearing cumulate layer is a thin one in orange here. Because there's so much titanium and iron in this layer, it's very dense, and it will sink into the already formed cumulates below, leading to a so-called overturn of the mantle. Melting of the titanium-rich cumulates could lead to the forming of a dense melt reservoir at the core mantle boundary that is seen in lunar seismology. And it could also lead to the forming of the titanium-rich surface basalts. But not too much is known about the melting behavior of this ilmenite-bearing cumulates at different depths in the moon. This study aimed to put experimental constraints on the amount of partial melt at certain pressures and temperatures. How this was done is I made my own ilmenite-bearing cumulate composition in the lab on the basis of the magma ocean crystallization work done before in Amsterdam. I loaded my synthetic sample in a very small 4 mm sized graphite buckets and assembly and put it in a piston cylinder press to pressures of 1, 2, and 3 GPa. Which correspond to depths in the moon of around 200 kilometers for 1 GPa, 400 kilometers for 2 GPa, and 700 kilometers for 3 GPa. The temperatures ranged from 1100 to 1400 degrees Celsius. After the experiments, samples were cut and polished and analyzed at the electron microprobe in Utrecht. In backscatter electron images, we could identify the different phases present in each experiment, and their chemical compositions could be measured. Using mass balance equations, the abundance of each phase could then be calculated. The images were also analyzed with a machine learning pixel classification program that was employed to assign individual pixels in the microscope images to different phases. Phase proportions were also obtained from this approach and then compared with the chemical mass balance approach. These are the phases found in each of the 15 experiments, spreading in a range of pressures, here on the x-axis, and temperatures on the y-axis. In terms of minerals, ilmenite is present in almost all experiments, here in green, with rutile only stable at higher pressures. You can see it in pink. Enstatite and orthopyroxene is present throughout, and pigeonite and clinopyroxene is present at higher temperatures, the orange one, and augite, a clinopyroxene with more calcium than pigeonite, is present at lower temperatures. Quartz is also present at low temperatures. Melt was found in almost all experiments, meaning that ilmenite-bearing cumulates would produce melts at all the temperatures given here on the y-axis. The melt percentage varies with different pressures and temperatures, as shown here. This graph has the melt percentage on the y-axis and temperature on the x-axis. It's quite a busy diagram, so I'll break it down. The different pressures.
We're not seeing a diagram.
You don't see a diagram?
No, we're still seeing the backscatter electron image.
Oh no!
I think there's a delay between when she is advancing the slides and when we're
seeing. Oh, I'm so sorry. Okay.
Now we see the colored version, so it's catching up.
Okay. So you didn't see the one with the minerals at all either. Okay.
Right now we see the color-coded backscattered image.
Okay.
Or at least I do. Okay, now we see the results, melt percent versus temperature, and
okay,
various pressures.
Just progress from there. Then maybe afterwards I can show it again if we still have some time. I'm so sorry, guys. So this is the melt percent on the y-axis and the temperature on the x-axis. I hope we all see that now. So The different pressures are represented by different colors, and the brighter colors are obtained from the chemical mass balance approach, and the duller colors are from image analysis. And as you can see, the general trend is that higher temperatures give more melt, and also lower pressures give more melt. But you can see that there are several deviations from this, particularly for the 1300 degrees Celsius experiments. We found very little mineral at 1 GPa and 1400 degrees, so we expect to be close to the liquidus temperature there. And we found almost no melt at 3 GPa between 1100 and 1150 degrees, and at 2 GPa at 1200 degrees, so we expect to be close to the solidus there. In general, the image analysis and mass balance approaches are in reasonable agreement, but we favor the mass balance approach because different cuts through the experiments could yield different percentages in the image analysis, while the mass balance is calculated for the entire sample. So I'm moving on to the next slide, so I hope it catches up with you guys. What does this mean? First of all, in many numerical models of the evolution of the interior of the moon, people use the solidus of terrestrial mantle peridotite as a measure for whether melting takes place. The peridotite melting curve. Oh, I'm so sorry. What did you say?
4 minutes left.
Yeah, thank you. So I hope you see the next slide now with the discussion, where the peridotite melting curve is sketched here. I hope you can see. The ilmenite-bearing cumulates, as you can see, melt much more easily than peridotite. Also, the study of Malik et al. From 2019, using a very similar approach to ours, found that as well. Our solidus temperature seems to be even a bit lower than Malik's work. In other words, the cumulus could produce quite a lot of magma in the moon, more than was previously thought. So in conclusion, we found that the solidus of the ilmenite-bearing cumulates to be at 1200 degrees at 2 GPa and between 1100 and 1150 degrees at 3 GPa. This means there is more melt in the moon's mantle than we previously thought. Future studies could perform similar experiments to this thesis at core mantle boundary conditions to explore the composition and density of the magma there. Furthermore, the results from this thesis can be incorporated in thermal models of the moon, and this will give us a better insight in the lunar interior. And lastly, the chemistry of the melt found with my experiments could be linked to the composition of the titanium-rich surface deposits. And I have a last slide if it's allowed. As I said before, this was my master thesis, and now I'm looking for a PhD opportunity. So if you know any in the field of planetary science, you can contact me here, and you can see my CV with the QR code if you want. Are there any questions?
That was wonderful. Thank you so much. And thank you for working through those technical difficulties. You did a wonderful job.
I'm sorry.
No, it's not your fault at all. Are there any questions for Marjolein? There's a question from Catherine Joy. What's the significance of the large amounts of rutile in your experiments?
Yes, I looked into that because I was wondering if you have more rutile, you would have less ilmenite because they both contain titanium, but that doesn't seem to be the case. It just is like an extra. I did find that if there is more rutile, there's less titanium left in the melt, so it might be less dense, therefore. If that answers your question a bit.
Let's suggest if there are any other questions, we can have those in the chat. And Marjolein, you can monitor the chat, see if any questions come up. But thank you so much.
Yes, thanks so much.